projects. In this video, we are going to explain about a project titled Detection of Supra Ventricular Arrhythmia using LSTM by LSTM and GRU. So now coming to the introduction part, the integration of deep learning models like LSTM, BI, LSTM and GRU holds significant promise for the automated detection of supraventricular arrhythmia. These models leverage the power of sequential data analysis to identify subtle irregularities in heart rhythms, enabling healthcare professionals to intervene promptly and provide appropriate treatments. As research in this field continues to evolve, further refinements and optimizations of these models are expected, ultimately contributing to more effective and accurate SVA diagnosis and management. By learning from historical ECG data, and LSTM models can identify subtle variations and abnormalities in heart rhythms, enabling early detection of SVAs and reducing the risk of complications. So now coming to the objective part for this project is to explore the application of LSTM, BI, LSTM and GRU neural network architectures for the detection of supraventricular arrhythmia. By leveraging these advanced deep learning techniques, the research aims to enhance the accuracy of SVA detection, compare the performance of different models, enable real-time monitoring and ultimately contribute to the development of more effective diagnostic tools for cardiac arrhythmias. This comparative analysis will shed light on the strengths and weaknesses of each model in the context of SVA detection. So now coming to the requirements part, we have two types of requirements, that are hardware requirements and software requirements. In hardware requirements, operating system as Windows is required, processor i5 and above, minimum 4 GB of RAM is required, hard disk 20 GB and above. Coming to the software requirement part, Python IDE that is 3.7 version is required. Now coming to the methodology part, first upload arrhythmia disease dataset. The first step in this process involves obtaining a dataset containing electrocardiogram signals related to arrhythmia diseases. This dataset should include a variety of heart rhythm patterns, both normal and abnormal, representing different types of arrhythmia. The dataset can be sourced from medical databases or research repositories and is essential for training and evaluating the deep learning models. Second, pre-processed dataset. Once the dataset is acquired, it needs to be pre-processed to make it suitable for training the algorithms. This involves several steps such as making or removing noise from the ECG signals, resampling the data to a consistent frequency, segmenting the signals into individual heartbeats, and normalizing the data to a common scale. Third, run GRU algorithm. Here GRU stands for Gated Recurrent Unit Algorithm. A type of recurrent neural network is then employed for arrhythmia detection. This involves constructing a GRU model using a training subset of the pre-processed dataset. Fourth, run LSTM algorithm. Similar to the GRU algorithm, the long short-term memory, that is LSTM algorithm, is implemented to detect arrhythmias. LSTM is also a recurrent neural network architecture that is capable of capturing long-range dependencies in sequential data. Run BI LSTM algorithm. Here BI LSTM stands for bidirectional LSTM algorithm. Extends the LSTM architecture by processing data in both forward and backward directions. This allows the model to capture contextual information from both past and future data points simultaneously. The BI LSTM model is constructed, trained and evaluated in a manner similar to the previous algorithms using in the pre-processed dataset. Sixth, all algorithms performance. After training, the evaluation and training, the performance matrix of all three algorithms are compared. These metrics include accuracy, precision, recall, F1 score, and possibly other depending on the dataset's characteristics. Performance comparisons helps in understanding which algorithm performs better in terms of correctly identifying arrhythmias and minimizing false positive or negatives. Seventh, predict arrhythmia from test data. With the trained models validated and their performance assessed, they are ready for predicting arrhythmias from unseen data. This involves feeding a test dataset, which the model have not encountered during training, into the algorithms for prediction. So now coming to the execution part. To execute the project, first we need to open the code folder. So here we have a folder which is named as dataset. In this they are containing some dataset over here. Another folder which is named as model. In this they are containing some .h5 files which can contain the deep learning algorithms information. These .h5 files can be loaded into the project code during runtime to utilize the trained model for various tasks, such as making predictions on new data or performing specific operations. Another folder which is named as test data. In these we are containing some data over here for testing. And this is the main Python file which is containing the Python script in it. And here this is the run.bat file. Instead of executing the program in command line interface, we created Windows bat file. So now to run the project, double click on run.bat file to execute the project. Here this is the graphical user interface with this we are interacting with the program. Now click on upload arrhythmia disease dataset button to upload the dataset. Here I am selecting this dataset folder and now click on select folder button to load the dataset. So now here dataset loaded, and you can see in graph that x-axis represents types of arrhythmia diseases and here y-axis represents numbers of records found for that disease. And so now closing this graph, now click on pre-process dataset button to replace missing values, normalized values, and then split dataset into train and test, and then we'll get the output. So here we can see dataset values are normalized, and we can see total records found in dataset as 138 over here. By scrolling down we can see this over here, and for each record contains 40 features, and we got here 80% accuracy for training, and data records as 110 and 20% test records as 28. So now train and test data is ready, and now click on run GRU algorithm button to train GRU for getting the output. So here on this screen you can see with GRU we got 75%, we got 92% accuracy, and in confusion matrix graph here x-axis represents predicted labels and here y-axis represents true labels, and the count in yellow boxes are the correct prediction and blue color boxes count are wrong prediction, and in graph we can see very few records are wrongly predicted. And now closing this graph, now click on run LSTM algorithm button to get the output. So here on this screen we can see LSTM we got here 92% accuracy, and in confusion matrix graph we can see total correct and incorrect prediction made by LSTM. All yellow or green boxes are correct prediction and blue boxes are wrong prediction. And now closing this graph, now click on run BI LSTM algorithm button to train BI LSTM for getting the output. So here again you can see that BI LSTM we got here 92%, we got 98% accuracy, and in confusion matrix graph also we can see more number of correct predictions and less number of incorrect predictions compared to other algorithms. So now closing this graph, click on all algorithms performance button to get the comparison output. So here you can see comparison table, we can see BI LSTM we got accuracy, and by closing this window, here in this graph we can see x-axis represents algorithm names and here y-axis represents different metrics such as accuracy, precision, and recall EBSCO in different color bar. And in all algorithms BI LSTM has got high accuracy. So now closing this graph, click on predict arrhythmia from test data button to upload test data for getting the prediction output. Now select this folder, click on select folder button, and here you can see in square bracket we can see test data, and after arrow symbol we can see predicted output as normal beat or supra ventricular beat is predicted. So by using deep learning algorithms we can predict or detect arrhythmia diseases. So now coming back to the conclusion part, in the broader context of medical technology, the integration of LSTM, BI LSTM and GRU models into clinical practice could lead to earlier SVA detection, reduced human error and improved patient outcomes. By providing timely alerts and actionable insights, these models empower healthcare professionals to make informed decisions and administer appropriate interventions. This diversity of capabilities suggests that a combination of these models or tailored selection based on specific clinical needs would offer even more comprehensive diagnostic solutions.
For updates on latest project videos, please visit True Project's YouTube channel and subscribe.